Chapter 18, Part 5. When we actually finally get around to talking in a little bit of depth about the Helvell-Hard-Zielinski reaction. Okay, I've made a big deal out of the fact that if you take an ester or any other acid derivative and you put it in acid, of course you protonate the carbonyl oxygen. That's a resonance stabilized protonation, because you can move the charge over to the other oxygen. And because of that, enolization of esters and amides and things like that does not happen. Now that's a good thing, because if you have an amide, especially like a secondary amide, and you could protonate the carbonyl, which is even more stabilized because the nitrogen resonance structure here is prominent even without the proton on the oxygen. If that happened, proteins, those things that make up most of your body, would enolize, I say E and Z, and you lose stereochemistry, and that would be a huge problem for life as we know it. So that doesn't happen either. So the question is, if you really wanted to make something like ethyl bromoacetate, how do you do that? How do you make bromoacetic acid? This is cheap. It's cheap because it's easy to make. You start with acetic acid, and even though you can't enolize this directly, you have to turn it into a surrogate of a carboxylic acid that can enolize. And what's the most reactive species, most reactive derivative of carboxylic acids? And that is the acid chloride, right? These are very, very reactive. There's very little resonance stabilization here because the P, if you put a P orbital on chlorine, it's really so large compared to the carbon that the resonance is very, very poor. And so that's doubly true if that turns out to be acyl bromide, an acid bromide. Now, in your text, we're treating this with bromine and phosphorus, right? That's an element. Very reactive, somewhat dangerous if you don't know what you're doing. But this combination, in fact, makes PBr3, and PCl3 takes carboxylic acids to, and alcohols to acid chlorides. So partly because the phosphorus-oxygen bond is so strong. So same thing here, you get PBr3, or if you're using chlorine, PCl3, you get the acid halide and acid. And under acidic conditions, we still protonate the carbonyl. And this is not stabilized. In fact, it's destabilized because you've got this electron withdrawing halogen. And so this will enolize. And when it enolizes, you have a very electron-rich alkene. And so in the presence of bromine, you get the alpha bromo acid bromide. And so it's easy. You know, you just need phosphorus. And in fact, this can be catalytic. So even if it's not so cheap, it's very cheap because bromine's cheap and phosphorus is used catalytically. And if you use it catalytically, you swap. The acid bromide reacts with the acetic acid, and you end up this reacts with, makes the anhydride, and it ends up making more acetyl bromide, and then that goes on to make more of that. And so you really only need a catalytic amount of phosphorus to take all the acid to the acid bromide, and then the acid bromide brominates, and then that reverts to the bromoacetic acid. Hope you could follow that. So, therefore, you can do this catalytically in phosphorus, or you can do it stoichiometrically. If you use it stoichiometrically, you get the acid alpha bromo acid bromide, and then you carefully add ethanol, and you end up with ethyl bromoacetate. Of course, you're generating all sorts of HBr, so even if you had used phosphorus catalytically, you're making a lot of HBr, and so you can do a Fischer esterification. Okay, and I guess I'll just use up the rest of the paper on that side and make the ester. So however you want to run that reaction, this takes you to the bromoacetate. So that's the Hell-Volhard-Zielinski. You need, it goes through an acid halide, and you need that acid halide, chlorine, bromine, those are really the only ones that are ever used. And under acidic conditions, that acid derivative will enolize. And that's the key, because esters don't enolize. All right, now let's talk about what else you can do with enols. Um, in the good old days, so if you take my favorite ketone, 2-methylcyclohexanone, and you treat it with sodium ethoxide, you will reversibly make the enolate, but you'll make 2 of them. And so which one, well, let's say, which one's formed faster? This one's formed faster because this is sterics. The base can get into that proton here a little more easily than this proton that's buried by all of this other organic here. However, these enolates are like alkenes. They're very much like alkenes. Take a C13 and you'll see that. Lower in energy, it's C13 NMR spectrum, that is. Lower in energy, so that's thermodynamic. Preferred. And so we like to think of this as the kinetic enolate, and this is the thermodynamic enolate. And if you do this with sodium ethoxide, you get about a 70-30 mixture. But if you do this with LDA, lithium diisopropyl amide, so take diisopropyl amine and treat it with a very strong base, because this has a pKa of about, let's see, I thought I looked that up in your textbook, 38. That's a very, very, very weak acid. So you need a very, very, very strong base. And typically we use N-butyllithium, which is really fast at doing this deprotonation, even at low temperatures. Lithium diisopropyl amine, or amide. And this is a bulky, non-nucleophilic base. And so this will give you the same enolate. And there's 2 differences here. Well, first of all, the ratio changes dramatically. You essentially get only the kinetic enolate. The enolate formation here is reversible with the ethoxy because you have ethanol in there as a proton source, and this is actually, not only is it reversible, it's really over on the side of the ketone, right? Because this has a pKa of about 20. HOET, it's a pKa of about, I'm going to go with their primary alcohol. I'll go back and say, yeah, oh, that's 16. So this is the ratio here of enolate to ketone is about 10,000 to 1. Okay, 4 orders of magnitude. LDA will take that proton off. The pKa differences are almost 18 orders of magnitude. That means you'll get this ratio and you're done. You'll get, it's all enolate. You usually use a slight excess to make sure there is no ketone remaining. And so that is, sorry, really important. This is a really important, you get 100% conversion. And if you want to control enolates and not have proton exchange, that's important. And we're going to talk about that next time. Thank you.